Hello, and welcome to my talk on Podman in HPC. I'm very happy to be speaking on HPC KP 21. My name is Valentín. I work at Red Hat in the Container Runtimes team. The Container Runtimes team is pretty much between the kernel and Kubernetes, with some overlap in both directions. So we take care that we manage kernel resources correctly. We implement tools such as Podman or Builder, Cryo, and Scopio, which I'm going to talk about in a minute. First, let me elaborate on Red Hat's containers philosophy. In a nutshell, we try to avoid one-size-fits-all solutions. We want to have use case, dedicated, and specialized tools. All of them that we're developing together with the community and other companies, they're built on open standards, namely the standards of the Open Containers Initiative, which cover the runtime aspects of a container, the image, networking, you name it. Everything we do is developed in the open, so you can pretty much look at my fingers on GitHub if you wish to do so. And Red Hat is 100% open source. So the container tools are no exception to that. Everything we do is 100% open source. While doing so, we take great care and have a real focus on interoperability and compatibility, not only for our tools, but also with other tools in the container ecosystem, such as Docker, Containerd. So all of them are supposed to, nicely coexist. An image created with Docker will run without any problems with Podman, Builder, and Cryo, and Scopio can copy it from A to B. To iterate a little bit on our philosophy, I really enjoy using this comparison or the analogy to Swiss Army knives. So the containerization started off really, with Docker, which somehow we see more on the left-hand side. Docker is great. The maintainers and the company have done a tremendous job on getting containerization started, on doing all these and implementing all these great features. But all of these features are really in one tool. So, you have hundreds of features that you can use, but those impact the non-functional requirements, such as performance, such as weight in terms of, bits and bytes, the size of Docker, the memory footprint is quite high, also the disk consumption. So in some cases, it's not very attractive. For instance, in automotive or in IoT, where a couple of megabytes can impact or mean a couple of millions higher costs in production. So same problem, or non-functional requirements or things that impact development. If I want to add a new feature, I really got to make sure that all other features continue to work. So for instance, if I only want to cut an apple, the left-hand side, it can be a little bit dangerous. At least I wouldn't be able to use this tool properly to cut an apple. So what I'm pointing at is, if we have a use case, sufficiently small use case, this is something where we want to position ourselves. Some tools do a better job than others, even ours. This talk is dedicated to Podman, and Podman aims to be a drop-in replacement for Docker. So Podman is also a quite heavy one, but we have other tools that really specialize in these use cases, which we would position more on the right-hand side, right? A small tool dedicated to a specific use case, tailored for the non-functional and functional requirements to somehow provide the best experience as they can. I also like to quote Alanis Morissette, when you've 10,000 spoons and all you need is a knife, we really want to provide this knife. So the Swiss Army knives that Red Hat started, the projects that Red Hat started and that we're now collaborating on with other companies and with the community, we have pretty much we categorized it into pretty much 4: to build, distribute, run, and orchestrate containers. So for building, we have Builder. For distributing, we have Scopio. Distributing really means copying images from A to B, transforming the image layers, changing compression, converting between the various image types, the Docker Schema 2 version 1 and version 2, or the OCI. There are various use cases that Scopio tackles. Most prominent one in the younger history is Scopio sync. This command allows for really syncing one registry with another one, or from a local directory, such as a USB disk. For instance, if you have an air-gapped environment, you plug in the USB stick, you copy these things to your on-premise registry, maybe air-gapped in this case as well, and you're good to go. This talk is dedicated to Podman, which covers the single node running use case. Podman can also distribute for sure, push and pull and build containers with Podman build. As I mentioned before, Podman is a drop-in replacement for Docker. For an orchestrated environment, like really in this case, it means Kubernetes, we have CRI-O. CRI-O has only a single purpose on this planet, and this is to serve the kubelet in Kubernetes as good as possible. The architecture in comparison to Docker, it's very, very different because, as I mentioned before, we really want to tweak it to these specific use cases. But I've been talking already, almost 7 minutes, so I'll try to increase my speed a little bit. Podman in a nutshell, it's short for pod manager. A pod is a term we inherited from Kubernetes, which pretty much is a group of containers, like an isolated object where these containers share certain resources, such as the network stack, network namespace, the PID namespace, things like that. The easiest way to migrate from Docker to Podman is a pretty old joke from our group, is just to alias Docker and Podman. And so far, I think that Podman is mostly known for its rootless support, which is something, from day one, Podman supported rootless containers. This means that we can execute and run containers as an ordinary user. Traditionally, Docker required to run containers as root. And this had some negative impacts on security, especially, for instance, in HPC. It's rather rare that users have root access on the machines. Also, the architecture of Podman differs compared to the one of Docker. While Docker implements a client-server model and runs as a daemon, Podman implements a fork exec model. There's lots of blogs and talks on that, and I don't want to speak too much on that. But there are certain advantages to that, because all containers are really, in Unix terms, child processes of the Podman command, of the initial Podman process. So it integrates better and adheres to the audit subsystem in the kernel. It integrates also better in a modern Linux system. For instance, into systemd, which is really something dear to our hearts, because we try to implement the containers are Linux, or follow this containers are Linux philosophy as much as possible, which pretty much states that a container is just an ordinary process on a Linux machine. So it shouldn't be special in any case, and integrate as good as possible into a modern Linux system. And I think Podman is great for sysadmins and developers alike. And I hope I can get my message across in this presentation. To iterate a little bit further on the compatibility to Docker, and for Podman serving as a drop-in replacement, there is a clear migration path if users already use containerization. Most of them will use Docker. Here, if you run Podman help, or many of the available commands that you see here are also available for Docker. There's one exception, which is auto update, where we can update running containers. I will talk later about this. This is something that Docker doesn't support. So there is many commands and features that we added to Podman that Docker doesn't support. Pretty much because it allowed us, to innovate and go different paths. The Docker maintainers chose different design decisions or didn't want to implement certain features that our users and customers were asking for. So for sure, we can run a container. We do a Podman run CentOS echo hello HPC KP, and we can run containers just as with Docker before. Image management is the same. Podman builds container images. Podman images lists them. Here, another example for building containers. You can use a Docker file, or Podman also supports a container file. Just to generalize a little bit on the terminology. And I've been talking about, daemons and root already, and this is, these topics are floating around all the time in the container space. So I wanted to make sure that the terminology is clear in this presentation. So as I mentioned before, traditionally containers were executed as root. There was the central Docker daemon, and if you run Docker run CentOS ls, the Docker binary that we're executing is not the daemon. It's actually, just a client tool that will communicate to the daemon via Unix socket, and the daemon in turn is running as root. Root was also, to be fair, really required initially to run containers. Many features such as networking require root privileges. Same for layered file systems such as OverlayFS. Just until recently, OverlayFS didn't run as a rootless user. It really required root. We have a tremendous engineer in our team, Giuseppe Scrivano, which implemented OverlayFS by means of a fuse file system, which allowed for running, OverlayFS is an ordinary user. So this was one way how Podman, implemented these features. Nowadays, on a modern kernel, Podman can make use of rootless overlay support, which is also faster because it doesn't have to run in user space. So, there are certain security risks or implications when we run as root, such as mounts and volumes. This means if you run as root and you share mounts with a container or volumes in the container, this container actually has root access to it. So if you share your home, the container runs as root, the container can change anything. So, common ACLs, will not hit much. Another thing, as I mentioned before, the auditing subsystem is one example where Fort exec model, just integrates better into the system. Since Docker is started by systemd, the login UID of the Docker daemon will be the overflow ID, something with 42 million or even more. I don't wear my glasses at the moment because they reflect, huge number that means nothing in the end. So what we see in the audit logs is we can see that a certain action has happened, but we do not see which user initiated it or invoked it. Well, with Podman, if I run a container and change something, I really see which login UID, which is unique for each user for the lifetime of this user, which allows for Podman to run in highly secure environments. In some cases, for instance, banks, insurances, or military-grade systems, security really systems. This is a strict requirement for running tools. So Docker wasn't or didn't really fit these requirements. And another side effect of root is, in the unlikely event of an attacker taking over the system by escaping the container, the attacker has root privileges on the host, and they can do whatever they want and even get rid of any traces. So this is something dangerous, which for sure also applies to Podman running as root or any other container engine running as root. So really, the daemon architecture and running as root cause certain problems in very restricted environments, such as HPC, multi-tenant systems in general, or, as I've been just elaborating on, the security-sensitive environments. So I mentioned before already the containers are Linux philosophy, where we really want to focus on a seamless integration into modern Linux systems. Running a container shouldn't be different than running just any other process on our machines. And a huge part of this integration of, getting Podman closer into a modern Linux desktop is the systemd integration, where, we allow and support Podman for running inside a systemd service. So you can create containerized systemd services, which is, a great way to run pretty much any kind of systemd services or workloads that you as an admin or as a developer have on your system. Another thing that we've been working on support for many years already is run systemd inside the container. So this was really a huge step forward in the ecosystem. Docker, for a number of reasons, didn't want to integrate it. But or support running systemd inside a container, but somehow the impact on customers and users is that they had to write manual startup scripts for their workloads to run inside a container, which is bad, because each and every time customer or these startup scripts vary across customers or vendors. It's hard to support, in some cases, many packages. If you do a DNF install HTTPD, well, they require these packages nowadays for many years, actually, require systemd. So for us as a vendor, this was perfect, because then users really don't need to worry about, am I running my workload in a container? Oh, if there's a container, I go on, I Google for a custom startup script that I copy somewhere from Stack Overflow. This is something that we as a vendor could not, really support. So nowadays there's no difference anymore. You can install it. Podman will auto detect and set up everything for systemd to run smoothly inside the container. There's a myriad of blog posts also online if you're interested in that. Otherwise, you can look at the man pages of, for instance, Podman generate systemd. We've seen auto updates before in the Podman help snippet that I shared a couple of slides earlier. This is a quite cool feature that built upon the systemd integration of Podman. And Podman auto updates, in a nutshell, will look up specifically configured containers. So the containers need to opt in to auto updates, and if a running container has been configured for auto updates, Podman will look at the registry, at the image that the container is using, check if there's a new one. If there's a new one, it will pull down this image and restart the container. So, this is pretty cool for edge and IoT use cases. And I'm pretty happy on, how and where it's used. The coolest example so far is, on that Podman is run offshore, which is an example for edge. It's really the far edge, pretty much, if you have your machines or your workloads running on the ocean. And it's pretty hard as an admin to just go there, plug a keyboard and do everything. Podman auto update is great because, you configure this thing, systemd is running, it triggers everything. There's a service and a timer that is pre-installed that you can configure by default. I think it runs at 10 a.m. in the morning. You just have to choose a random time, and you can configure everything. Future plans are to implement simple rollbacks, and they're coming soon. Another thing that I want to highlight for Podman is, as I mentioned earlier, when we were talking about these 4 use cases, Podman is focusing on a single node. Podman will not run in an orchestrated environment. That's not what it's designed for. That's cryos, really. That's cryospace. But we wanted to make sure that there is an easy bridge between the single node, more traditional way of running your workloads, or even a local development machine, your workstation, to the orchestrated Kubernetes space, the cloud native space. So Podman allows for running, Kubernetes YAML file that you would traditionally, feed to kubectl, and spin up a bunch of containers and pods and run the workload. So this is pretty cool. So, if you want to, develop a certain Kubernetes service or workload, you do all this complex YAML stuff, you set everything, you want to test it, but you may not have access to Kubernetes cluster, or you got to pay for it because it's, I don't know, in a public space, public cloud provider. You got to pay for all cycles that you consume. Podman PlayCube is an awesome way. You can develop locally. The other way around, you can also use Podman Generate Cube to generate such Kubernetes YAML file, and lots of people do it because these YAML files are complex. I keep forgetting all these different formats because there's JSON, there's YAML, there's TOML. It's a nice way to get started, migrate your workload from your local machine to an orchestrated environment. There's also a Restful API. So far, all the slides that I've shown, we looked at the command line interface where Docker and Podman, or Podman is compatible to Docker, but there's also the remote API. Pretty much when the API that the client uses to talk to the daemon, the Docker daemon. Since Podman version 2, Podman has also a REST API that is compatible to Docker. So this is really fulfilling the promise of running as a drop-in replacement. So if you have workloads that use the Docker RESTful API, now you can just point it to the Podman socket, and you're done with it. So this really fulfills the aliasing promise that I mentioned earlier. And since Podman 3.0, we also support Docker Compose. There were a couple of things that Docker Compose really needed and relied on that we needed to massage into Podman, mostly networking related, but we got there, and now you can use Docker Compose on Podman. So this is pretty cool. And now since Podman version 3.2, which we just released, I think last week, this also runs rootless, which is pretty cool. Another thing before going deeper into the HPC use cases is the advanced image management of Podman. As I mentioned before, we really tackle the use cases separately, and when you have a look at the code, we have a couple of core libraries that we implement for managing the container storage, also for managing images, doing all these conversions that all the tools also share. So there's the container storage library, the containers image library, which in turn is used by Cryo, Scopio, Builder, and Podman. And there's a lot of cool features. In containers image, most of these features are configurable or exposed to the user, to the developer, or admin via the registries configuration file, which is in etc containers. And one use case that emerged, or immediate use case that emerged late last year, was when Docker Hub introduced a rate limit. Pretty much it started on November 2. Unless you're logged in, you're allowed, or a given IP address is allowed to only do 200 container pulls in a time frame of 6 hours. If you exceed, the registry will reject the request. If you're logged in 600, everything above, you pay. And by no means, I'm not criticizing Docker Hub at all for doing it. I'm actually surprised how long somehow they allowed the world to use these things for free, but it also had some very real consequences for many people, because Docker Hub was used in many testing systems and in the CI infrastructure, including our own. So pretty much in a very short time frame, in a matter of minutes, our CI hit these limits. So we needed to make sure that we have a path forward. One path forward is mentioned here in the slides. If you configure the registries conf file with a snippet below, it will just work. What's happening under the hoods is that we set the prefix to Docker IO, and then we configure a specific location, which can be a container mirror.org. We use the mirror of GCP. What happens underneath is that when we pull an image from docker.io, it will actually be pulled from this specific location. So we had the immediate benefit that we didn't have to look for all places in our CI that potentially referenced an image on Docker Hub. This is a very tedious, manual, and error-prone task. It would really have turned into a whack-a-mole, but instead we just had to add 3 lines to a config file, and we're all done. Thanks to the pretty powerful advanced image management capabilities of all these tools. So let me dive a little bit into Podman and HPC to put these things a little bit more into context. Until now, I was talking a lot about rather introducing Podman and the tools, the philosophy behind things like image management that I just talked about, the capabilities to bridge to Kubernetes, the architecture of Podman, which is a fork exec model. It runs rootless. There's many spaces that we innovated in, and HPC is one of them. So Podman didn't start as an HPC or a container engine for specifically tailored for HPC, such as Singularity, which does an awesome job. So we came somehow from a more general purpose background, and a couple of years ago, I think 3 years ago or so, the HPC community started to look at Podman, pretty much for the aforementioned reasons: rootless, the architecture, it's independent, community-driven, and they could contribute to Podman and all the libraries. And we, as the maintainers, we try to look at the HPC requirements, and still do, and try to generalize these in a way that Podman and other users benefit from it as well. So if you want to run Podman in an HPC environment, there's a couple of things that are, that you may need to do in order to run in your specific environment, but they're pretty straightforward. There's many blog posts out, a couple of talks you can find also on YouTube. And if there's something you need that doesn't work, please feel free always to reach out to us. So as I mentioned before, we started collaborating with the HPC community all early on, and rootless support and the daemonless fork exec architecture are crucial. These are really the cornerstones for Podman to be able to run in an HPC environment. Podman supports running in MPI. There's a great blog post from, from 29 by Adrian Reber, a tremendous colleague and engineer at Red Hat. But Podman also runs on Slurm. There are similar tweaks needed as described in the blog post. Myself, I do not have really an HPC background. As I said before, I'm more an operating systems person, and we collaborate together with the HPC community, with customers and users, to get Podman to play nicely with all these schedulers and tools that are developed and exist in the HPC world. So rootless Podman is implemented via user namespaces, and these user namespaces are very important to understand how we can get Podman to run in an HPC environment. So I don't want to go too deep into user namespaces, just scratch it on the surface. What's pretty much a user namespace, what it's pretty much doing is it allows for mapping, create a new user ID and group ID mapping. It creates a new namespace, which allows, for instance, for a rootless container. If I run it as an ordinary user on my Fedora workstation here, I have UID 1000 inside the container. The process and the user, can be pretty much any UID, even root. User namespaces allow for doing that. And by doing so, it allows for running containers even in highly restricted environments such as HPC, because a single mapping, which I'm going to talk about in a couple of slides, is also possible. So if we run Podman, we do a Podman run -- user 10, which instructs Podman to create a user namespace and the initial UID with an initial UID of 10. So we run a container and we just sleep until infinity. If I then run Podman top and I query for the user ID on the host and the user ID inside the container, we can see that, well, the user is 10 inside the container. On the host, it is user ID 100K9. 100K9 comes from the UID mapping that is set up in the etc sub-UID file. If you're interested in that, there's a couple of talks out and blog posts, and it's also explained in the main Podman man page. So go check that out if it's of your interest, how these things are set up underneath. The single UID mapping that I mentioned before can be set up by using the -- user ns option and use the value keep-id. What it does is it maps the current UID and GID into the user namespace of the container. So in this case, we wouldn't have 100,009 and 10 as before, but 1,000 and 1,000, which would mean inside the container we have the same UID as outside. This is pretty cool because it doesn't require set UID and set GID privileges, which is required in some HPC setups. And it also allows for, if you mount your home directory inside, you don't have to worry, or does this new UID have access to it? How about SE Linux and all these things? It'll just work. You don't have to worry about it. And this is a very, very portable way of running your container. However, there's one problem, especially for portability. It may depend on the point of view. The thing is that many container images use more than one UID and GID. Makes sense for security reasons, because we want to have access controls. However, the counterpart for the registries conf, which is for images, there's a storage conf, which also lives in etc containers, and it has a solution for it. There's a specific option which is called ignore shown errors, which by default is set to false, but we can set it to on. And I'm just going to read out loud the explanation. Ignore shown errors can be set to allow a non-privileged user running with a single UID within a user namespace to run containers. So as we said before, the somehow fits inside. We have a single UID within a namespace to run these containers, which pretty much happens when we use keep ID. The user can pull and use any image, even those with multiple UIDs. Excellent. This is exactly the problem we want to solve. However, we got to note that these UIDs necessarily, the natural consequence is that we will flatten the UID and GID space down to a single one, and these images will have no separation between, the users in the container. So this is pretty much the necessary evil, but a very portable way. And it was in fact motivated by HPC use case, and it was a community contribution by HPC users and customers. So this is a very nice way. The cool thing is that this allows also for running Podman on NFS. So let's check this out. So NFS volumes for containers, Podman, they just work well, no big problem. The really challenging part is the container storage. And well, we've been chatting about user namespaces just before, but NFS does not support user namespaces. So if we, think back to the example of where we wanted to run this user 10 inside the container, what the NFS server will see is that we try to chown the files as this host user, which is 100,009. And the NFS server will say, well, I have no freaking clue about this user ID. I don't know it. Well, the request is invalid, and it will throw back an error. We do not have this problem if we use user as a keep ID. This will just work. There's a so, in this case, the user ID will be the same inside and outside the container when we want to chown. And the NFS server will know that, oh, yeah, Valentín is allowed to use this UID. I know this UID. Everything is fine. And the request will work. Container storage can live on NFS shares, no problem. There's a couple of cool more recent developments, especially in the kernel, which just recently added extra attribute support to NFS, which is pretty cool. So Podman and Fuse overlay FS allow now for user as support. What's happening underneath is that Fuse overlay FS, which is the tool I mentioned earlier by the colleague Giuseppe Scrivano, the tool that implements overlay FS in a Fuse file system so it can run as an ordinary user. What it does is all the UID and GID mappings are stored in extra attributes, and then they're chown in the Fuse FS that is running in the user space. So this is a pretty cool way and pretty smart way, I find, to get support where it is now. But this is something that needs to bubble up into the products. I think starting with RHEL 8.5, you can play with it. You can also play with it in Fedora, but commercial products and NFS servers do not yet support it. This is just something where we need to be patient, but it will land at some point in the future. Workaround. If you really want to make use of full user namespaces, and if you have NFS, well, then workaround maybe to just move the rootless container storage off NFS. For instance, you can put it into var temp or any other directory that supports it. Some file systems are less recommended as others, but this is a way to work around the problem. But in many cases, or at least in my experience, most HPC customers and users, they say, awesome, user as keep ID will solve all our problems, and they're off to go. So if you're interested, how would you get Podman? On Linux, it's pretty easy. It's also easy on Windows and Mac, but on Linux there's all these distributions, and Podman is now in the main repositories of pretty much all of them. Maybe Fedora, CentOS, Debian, Ubuntu, OpenSUSE, Arch Linux, Gentoo, Manjaro, and also the enterprise counterparts. Red Hat Enterprise Linux, SUSE Linux Enterprise, Amazon Linux. You name it, you install it, you're good to go. And we also provide binaries for Windows and macOS. You can download these binaries either from the release page in GitHub. You can use Homebrew for macOS. It requires, however, a Linux machine. Containers will be or are a Linux concept. So if you run it on Windows or macOS, you actually use what we call Podman Remote, which will send commands via the REST API to a remote Linux machine. This can be a server in your basement or in the server room of your company, or a virtual machine that you run on your desktop. So currently we're working together with the community to allow for an easy setup of these virtual machines. And starting with Podman 3.2, there's a new command also, which is called Podman Machine, which allows for setting up and creating and managing those virtual machines. So it will install a Fedora Core OS machine, virtual machine, set it up, and do everything for you. We'll take care of networking, all these things. Brent Bowdy, the Podman architect, did a tremendous job on getting this done. So if you're interested, I want to encourage you to try it out and let us know what you think. So I'm pretty much hitting the 40 minutes now. This is the last slide. Further reading. So the team and also the communities, we're pretty active at blogging. So if you are interested in any of the topics or want to be up to date, there's podman.io, which is a blog, and where we also point to blog posts and other resources such as redhat.com, sysadmin, opensource.com, developers, redhat.com. And if you're extra curious or have an issue or a feature request, always feel free to reach out on github.com containers podman. We also have IRC channel on LiberaJet. We're also reachable on the official Matrix server. All of these resources are also linked on podman.io. So now I'm happy to answer any questions. Thanks.